Many of the early Mathologer videos had a movie hook. E to the I pi in The Simpsons, the Die Hard Jugs puzzle, the Futurama mind-switching theorem, etc. During that time I also started working on a Doctor Who based video, but halfway through writing the script, 3 Blue 1 Brown published a video on something related. Not the same, but close enough to effectively kill the topic for a while. Happens sometime. Anyway, I just stumbled across that old slideshow, and since I've got absolutely nothing else going on right now, what a joke, semester about to start, I decided to finish it. It's some really nice material, starting with the super famous Tower of Hanoi puzzle, but ending up well off the beaten track. I think I first encountered the usual Tower of Hanoi stuff in primary school, but then throughout my life I've learned about many other amazing aspects of this puzzle. Today I want to tell you about some of my favorites. Among other things, I'd like to tell you why the unlikely fraction 466 divided by 885 is the Tower of Hanoi constant. And I'd like to show you a super pretty and super visual shortest solution of the so-called Reve's puzzle, which is the 4-peg version of Hanoi. That one there. And I'll also talk about the so-called Frame-Stewart algorithm, which is believed to give the shortest solution for all Hanoi puzzles for any number of pegs. However, although this algorithm is very natural, some expert algorithmologists, yeah, that's a word, believe that nobody will be able to prove that this supposedly shortest solution really truly is always shortest. Intrigued? Great, off we go. But first, Doctor Who and a matter of life and death. In one of his 1966 adventures, the Doctor and his friends are captured by the powerful celestial toymaker, and they're forced to play a number of life and death games involving some devilish toys. The Doctor's game is an instance of the Tower of Hanoi puzzle. Here's a reminder of how you play this game. There are 3 pegs and a number of discs that can slide onto each peg. The discs start out stacked in a tower. The object of the game is to move the tower all the way to the right. And nope, you can't just take all the discs and plop them on the right peg. That wouldn't be much of a puzzle, wouldn't it? The rules are that you can only move 1 disc at a time, plus a larger disc can never be placed on top of a smaller disc. Let me just show you a few moves using the setup over there. What should you do next? Well, you cannot do this. Why? Because here a disc ends up on top of a smaller disc, which is against the rules. On the other hand, this is possible. And this one, and that's also possible here. All clear? Great. Here's the setup in Doctor Who. The pegs are invisible and located at the corners of an equilateral triangle. There are 10 discs, and to win the game, the Doctor has to move the tower to position B in exactly 1023 moves. The toymaker refers to the puzzle as the trilogic game. Whatever. Sounds impressive, right?
I think you will lose. Can you remember how to play? I am only allowed to move 1 piece at a time. That is right. And you must rearrange them in the same order that they are now on point C. And I am not permitted to put a larger piece on a small piece. Correct.
Ah yes, the good old times. Anyway, it turns out that the toymaker permitted the Doctor just enough moves to solve the puzzle. 1023 is the minimum number of moves to be able to relocate the whole tower. And there's a unique sequence of moves to do it. The Doctor cannot afford to make a single move out of order or he'll lose the game. And for his life. Okay, there will be a lot of you who are very familiar with the Tower of Hanoi. But if you were in the position of the Doctor right now, would you be able to play those exact 1023 moves without messing up? No? I thought so. And without a clear recipe in hand or in mind, I doubt I could either. So let me first quickly show you or remind you why the minimal solution has exactly 1023 moves and how you can easily execute these moves without ever messing up. And then, if you're ever captured by an evil toymaker, you will be ready. Okay, the key to this puzzle is to notice that for us to be able to move the largest disk anywhere, we first have to transfer all the smaller disks to another peg. For example, to that one. There. With the other disks on the middle peg, we can now move the biggest disks to the right peg. And actually, at this point, we can complete the transfer of our tower by moving the smaller disks again. All right. How does this insight help? Well, let's see. In this instance of the puzzle, there are 10 disks, just like with Doctor Who. Let's say that M9 is the minimum number of moves required to move the little 9-disk tower. Then we can definitely transfer the whole 10-disk tower using M9 moves, there are those, plus one move, plus another M9 moves. Okay. With M9 being the smallest number of moves to transfer a 9-disk tower, we found that we can transfer the 10-disk tower using that many moves. But can we do any better than that? What do you think? Well, the answer is no. Pretty obvious, isn't it? If we deviate in any way from our simple overall strategy to transfer the tower, we are bound to use more moves. So what we figured out is that the minimal number of moves to shift 10 disks is exactly this. Of course, everything I just said works for any number n, not just 10. Right? And so now, to figure out M10, we just go back up. Okay, what's M1, the minimal number of moves to relocate the little disk? Tough one, huh? M1 is equal to, well, 1 of course. There, one move. Okay, and now we just plug M1 equal to 1 into the formula to get M2. There, 2 times 1 is 2 plus 1 is 3. Great. And just to check, there, 1 move, 2 and 3 moves in total. What are those numbers? M1 is 1, M2 is 3. What's next? Well, 2 times 3 is 6 plus 1 is 7. M3 is 7. Then 15, okay, 31, 63, 127, yeah, looks familiar, right? 255, 511, and there. M10 is 1023, just like the toymaker planned. And what are these M numbers? Pretty obvious, right? These are just the powers of 2 minus 1. In the case of 10 disks, it's 2 to the 10 minus 1 is 1023. And of course, it's blatantly obvious that this works in general. The minimal number of moves for n disks is 2 to the power of n minus 1. That's clearly the pattern. And can we prove it? Yep, it's an easy induction thing. Once we know mn equals 2 to the power of n minus 1 for some n disks, our stepping formula tells us that mn plus 1 is 2 times that plus 1. And a little jiggling the number gives this. Works. The same formula. So, knowing the answer for n disks, our stepping formula tells us the answer for n plus 1 disks, and then we get n plus 2 disks, and so on to infinity. So it's all proved. It's also not too hard to show that there's just one sequence of moves that will work for this minimum number. How can we see that? Well, again, we can argue from the bottom up. Right? There is just one way to transfer that one disk to the right using one move. What about 2 disks? The unique minimal way to move the smallest disk to the middle peg, together with this move, together with this second unique minimal way to move the smallest disk to the right, combine into the unique minimal way to move the 2-disk tower. We can continue arguing like this to convince ourselves that there are unique ways to transfer all the towers with different numbers of disks. There, unique, unique, unique. Okay, now you're Doctor Who and you have to make just the right 1023 moves without messing up a single time to move the tower. One way to get such a recipe is from a detailed analysis of the sequence of moves. This yields, for example, some beautiful relationships with binary counting, which is the topic of the 3 blue 1 brown video. I'll put a link in the comments. Another way to get a good feel of what's going on is by experimenting with smaller stacks. Let's say we've done this for a while and we figured out the complicated sequence of moves in the case of 6 discs. Now let's step back and just observe the sequence playing out in the Doctor Who setup, viewing it from above and with the pegs placed at the corners of an equilateral triangle. See whether something jumps out at you while watching this pretty dance of discs. Did you notice a simple pattern? Yes? No? Have another look, but this time pay attention to the smallest disc. So what happens is that every second turn we move the smallest disc, and we always move the smallest disc in the clockwise direction. And believe it or not, these two insights that all you have to remember to reliably execute all 1023 moves. That doesn't seem right, does it? What about all the other discs? How do we know what to do with them? Well, let's have a close look. Okay, first the smallest disc moves in the clockwise direction. What comes next? Well, we're not moving the smallest disc on this turn, and so there is only one possibility, this one. Okay? What's next? Well, it's the smallest disc's turn again. Moving it in the clockwise direction, we get this. Okay? Again, we're not going to move the smallest disc. So again, that leaves exactly one choice, this one here. And so on. Move the smallest disc clockwise. Make the only possible move that does not involve the smallest disc. Move the smallest disc. Make the only possible move that does not involve the smallest disc. And so on. Really easy, isn't it? It turns out that if you follow this recipe, you end up moving the tower to the position at the bottom left. What do you have to do if instead your task is to move the tower from its starting position to the bottom right? Think about it for a moment. Got it? Yep. Just move the smallest disc in the counterclockwise direction instead. Pretty obvious, right? Now, the simple recipe for executing the optimal move sequence in practice works for any number of discs. And it's actually very easy to prove that this is the case, given the recursive nature of the algorithm. The only thing that may change is the direction in which you have to move the smallest disc to ensure the tower ends in the bottom left or right. Okay, back to you putting yourself in the shoes of the Doctor. Which way do you have to move the tip of the tower to make sure that the whole tower ends up in position B? Clockwise or counterclockwise? Remember, your life depends on it. How about in general? If you're dealing with n discs, which direction does the tip have to move to relocate the whole tower from A to B using the minimal number of steps? Leave your answers in the comments. Now you should really give this a go. Get 5 or 6 coins of different diameters and execute the algorithm. Go on, I'll wait. Okay, no, actually, forget about it. Did you mess up? How does the second largest disk move? How about the third largest disk? Also share your observations in the comments. Nice stuff there. Finally, back to the original tower with this side-by-side setup. To get the whole tower to the right peg, what's the rule for moving the smallest disk? Easy, right? Now, before I move on to the main attractions, my visualization of optimal solutions of the 4-peg puzzles and the elusive frame-Stewart algorithm, let me share some really cool insights about the original puzzle with you that very few people know about. Okay, from this starting position we can execute one of 2 moves, both with the smallest disk. These moves get us to two new states of the puzzle, those two here. Where can we go from these new states? Well, by moving the smallest disk, we can move between these two states. We can also move to two new states. All right. If we systematically continue this picture, we eventually arrive at this so-called transition or state graph. Whoa! The vertices of the state graph are all possible states of the Hanoi puzzle. And two of these states are connected by a blue edge exactly if there is a move that takes one state into the other state. Pretty, huh? For 4 disks, the graph looks like this. Cool. For 5 disks, it looks like this. Okay. And so on. These graphs are closely related to the Sierpinski triangle, which you may be familiar with. But that's a story for another day. Let's get back to our 3-disk state graph. That one there. The starting and end states of the puzzle are at the top and at the bottom right corner of the graph. Those two guys. The shortest sequence of moves between the starting state and the target state corresponds to a straight line connection. Nice, huh? And in general, any path like this corresponds to a sequence of moves that takes you between the states at the ends of the path. Here are a couple of fun facts hiding in the state graph. Have a look at this. This path visits every state exactly once. That's pretty neat, and it's definitely a contender for the new torture puzzle if the celestial toymaker is looking for ideas. And what's extra nice is that there is also a simple way to remember this convoluted solution, very similar to the way we remember the shortest path. Have a look. It goes like this. Move the smallest disk to the right once, then twice. Make the only move that does not involve the smallest disk. Move the smallest disk left once, twice. Make the only move that does not involve the smallest disk. Now repeat. Smallest disk moves right twice, other disk. Smallest disk left twice, other disk, and so on. Very nice, huh? And this recipe works for any number of disks. Small, right, right, other disk. Small, left, left, other disk. Small, right, right, and so on. This recipe also solves another Hanoi puzzle. Add one more rule to the game, that you can only move disks between adjacent pegs, right? So you're only allowed to move between the left and middle peg and the middle and the right peg, but never between the left and right peg. Then what you see over there is the shortest sequence of moves that takes you from the starting to the end state. Challenge for you, what's the formula for the number of moves in this new shortest solution for the n-disk puzzle over there? A very pretty answer awaits. Okay, here's another interesting variation of the Hanoi puzzle. Pick any 2 states. Now find the shortest sequence of moves between them. Here's one, it consists of 6 moves. However, shortest sequences between states are not always unique. Like in this example, here's the second shortest solution. Also 6 moves. Okay, here's something really amazing. Do this. Choose a starting state and an end state and calculate the minimal number of transition moves. Then find the average of all these numbers. Believe it or not, but somebody actually managed to find formulas for this average minimal length, and it looks like this. Whoa, pretty insane, right? Plug in 3 and you get approximately 3.9 moves. Okay, so what? 2 observations. These 3 numbers, the ones being raised to the power of n, are all less than 1. And what happens if you take a number less than 1 and raise it to a large power? Yep, it gets tiny. This means that all these powers tend to 0 as n goes to infinity. Okay. Now, by way of comparison, it turns out that the maximum minimal length, that is the maximum possible distance between any 2 states, is our 2 to the power of n minus 1 from the 4. That one there. That is, you can get from any state to any other state with at most 2 to the power of n minus 1 moves. Okay, so look again. The 2 to the power of n's dominate both expressions for large n, and therefore for large n the constants minus 1/3 and minus 1 are negligible. So what this tells us is that given a large number of disks, the average minimal length is approximately the 466 over 885 of the maximal minimal length. And this makes 466 divided by 885 into something like the Hanoi constant. Yep, 466 divided by 885. Pretty bizarre, isn't it? I'm sure you didn't see that one coming. Here's a nice puzzle for you. Remember, when you plug 3 into this formula, you get approximately 3.9 for the average minimal distance. Now, obviously, the exact number is a fraction, right? Can you figure out what this fraction is? Leave your solutions in the comments. So the original 3-peg Tower of Hanoi puzzle was published by the French mathematician Edouard Lucas in 1883. It's interesting to note that Lucas' version of the puzzle actually features the pegs arranged in an equilateral triangle, just like in Doctor Who. Lucas also considered variants of the puzzle featuring more than 3 pegs. Here's a picture of what he had in mind, which he published in 1889. All right. Now, the person who usually gets the credit for Hanoi puzzles with more than 3 pegs is the English puzzle master Henry Dudney, who first talked about these variants in 1896. Keen Mathologer fans will recall that we've encountered both Lucas and Dudney previously. Among other things, Lucas is the Lucas in Lucas numbers, the famous relatives of the Fibonacci numbers, and Dudney was the author of that tricky puzzle Ramanujan solved at a glance with an infinite fraction. We just covered the Ramanujan story in a recent video. Some of Dudney's Hanoi puzzles also made it into his famous puzzle collection entitled the Canterbury Puzzles. The very first puzzle in this collection is a 4-peg puzzle, and I guess it's this prominent position in this famous puzzle book that ensured serious exposure for Hanoi puzzles with more than 3 pegs and led to Dudney being credited as the inventor. Okay, here's Dudney's framing of the puzzle. There's this group of pilgrims. One of them, the Reve, is a smart guy who, during a rest in a town, challenges his fellow pilgrims with a 4-peg Tower of Hanoi puzzle. Here the pegs are 4 stools and the discs are cheeses of varying diameters. Specifically, he asks for the minimum number of moves to transfer cheese towers consisting of 8, 10 and 21 cheeses. As part of the solution to the puzzle, Dudney discusses solutions of Hanoi puzzles with 3, 4 and 5 pegs, and among other things produces this very interesting table. For example, with 4 stools and 10 cheeses, he claims the minimal number of moves is 49. 49, that's way less than the 1023 we needed using 3 pegs in the Doctor Who setup. On close inspection, Dudney's table hides some surprises. For example, our magical 1023 also appears in this table as the minimal number of moves required in the case of 5 pegs and 56 cheeses. Also, have a look at the special numbers of cheeses Dudney singles out in his table. In the case of 4 stools, he considers the numbers 1, 3, 6, 10, 15, 21 and 28. Well, the regulars among you will recognize these numbers straight away. These are just the triangular numbers. Numbers that can be written in the form 1, plus 2 is 3, plus 3 is 6, plus 4 is 10, and so on. For 5 stools, the numbers Dudney considers are these numbers of cheeses. These are the so-called tetrahedral numbers, the numbers you get when you add the triangular numbers. 1, plus 3 is 4, plus 6 is 10, plus 10 is 20. And I've got to get these tetrahedra there. Okay, before I say anything about how Dudney and others attacked the Hanoi puzzles with more than 3 pegs, let me jump straight to one of the highlights of this video. I want to show you an easy to remember and visually stunning method for solving the 4-peg Hanoi puzzles using a minimal number of moves. Perfect, of course, for your next encounter with the toymaker. Okay, suppose we start with 6 gray discs and 4 blue pegs arranged like this. 6 is equal to 1 plus 2 plus 3, and so 6 is a triangular number. Arrange the 6 discs into 3 super discs like this. The smallest disc is the first super disc. Then the next 2 discs together make up the second super disc. And the remaining 3 discs form the third super disc. 1 plus 2 plus 3 is equal to 6. Now we can just use the outer 3 pegs and the usual 3-peg solution to move the superdisk tower around. Remember, in this solution, the smallest red superdisk moves clockwise and all the other superdisk moves are forced. There, 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 there. Cool, but now we add the details. Let's do this again, but we'll also show the moves of the individual disk within the superdisks. That will ensure the whole sequence is a legitimate puzzle solution. Okay, red disk moves clockwise. Now the green superdisk is supposed to move here. We do this 1 green disk at a time using these 3 pegs and the usual 3-peg algorithm. There, there, there. The green superdisk has completed its move. This means it's the little red disk's turn. There, and it goes. Now the orange superdisk is supposed to move here. We do this 1 disk at a time using the 3 pegs and the usual 3-peg algorithm. Okay? This means that again the smallest orange disk moves clockwise. 1, 2, 3, 4, 5, 6, 7 moves. Okay? And by now it should be clear how this continues. Orange superdisk has finished moving, little red disk moves. Next the green superdisk moves here. Okay. And it goes. There, 1, 2, 3. And finish. Excellent. A very pretty solution, don't you think? The intertwining of several optimal 3-peg solutions gives the optimal 4-peg solution. The next triangular number after 6 is 10. So just for fun, here's the complete sequence of moves for 10 discs. If you count along, you can convince yourself that the number of moves is really 49 moves, indicated in Dudney's table. Fabulous! It's also easy to adapt this procedure if we don't deal with a triangular number of discs. For example, let's get rid of 2 of the 10 discs over there and we're left with 8 discs. 8 is not triangular, but is also one of Dudney's puzzle numbers. There, 8 discs left over. Create super discs as before, 1, 2, 3, etc. Now that last purple super disc only consists of 2 discs. We get rid of this defective superdisk by adding 1 disk each to the last 2 superdisks. There, the green superdisk gets 1 more disk, okay, and the orange one also gets 1 more disk. From now on, everything proceeds as before, except that the top disks of the modified superdisks always move counterclockwise. Just quickly, let's also run through this example. Great. Challenge for everybody, figure out the minimal number of moves for 9 discs. Leave your answers in the comments. For my programmer friends, please implement the algorithm I just showed you for general N. Should be fun. Dudney claimed the numbers in his list to be minimal. An actual proof that he was right in the case of 4 pegs was only produced recently, 100 years later in 2014, by mathematician Thierry Bouche. Combining his proof with the work of others yields that the solution I showed you is optimal, all a bit involved and much more complicated than you'd expect knowing the simple solution for 3 pegs. And what about 5 pegs? That was proved in, well, it actually hasn't been proved. For 5 pegs and more, we have Dudney's and other candidates for optimal solutions. However, there is no general proof for optimality in sight yet. In fact, Donald Knuth, the algorithm guru himself, once said that even if it's true that these solutions are optimal, most likely nobody will ever be able to prove it. Well, Thierry Bouche did prove it for 4 pegs, so maybe there's hope after all. The idea for finding optimal solutions for a certain number of pegs and disks is to base it on optimal solutions with less pegs and or disks. It's actually quite simple. Let me show you. Say we've already figured out the optimal solutions and numbers in this table, and we're interested in the solution for 4 pegs and 7 disks. That number there. Okay, split these 7 disks into 2 parts. Let's say into a blue stack of 2 and a green stack of 5. Now we can move the green 5 disk stack using all 4 pegs with 13 moves. Okay. Now we can move the blue stack of 2 disks using the remaining 3 pegs with 3 moves. Finally, we can move the green stack again using all 4 pegs with another 13 moves. In this way, we've moved the stack with 13 plus 3 plus another 13 moves. That's a total of 29 moves. Not bad. Can we do better? What do you think? Well, we can split the original stack in different ways and see what happens. Repeating the calculations for all possibilities, we get these numbers here. Okay, that's worse. Oh, best so far, okay. Just as good. Worse. Or even worse. So 25 is the best we can do this way, and it turns out 25 is best overall. Okay. All this then also explains where those super disks come from, right? One of the super disks for our super pretty move sequence for 7 disks is just this layer of 4 blue disks at the bottom. By arguing in the same way, we can keep extending our table of numbers to the right. And once enough numbers in one row have been built up, we can start building up the next row from the trivial cases involving the smallest numbers of disks on the left. All in all, a pretty straightforward idea, which definitely gives very short solutions. The algorithm that I just described is called the Frame-Stewart algorithm. It's generally believed that this algorithm will indeed produce minimal solutions for all possible numbers of disks and pegs. However, how do you prove that these solutions are actually shortest? Well, to begin, and as usual, you can run some exhaustive searches for small numbers of disks to check your conjecture. People have done that and everything pans out so far. Then you can go pattern hunting in the algorithms to see whether there are enough clues upon which to hang a proof. Examples of such patterns are the splitting of move sequences into superdisks, the special role triangular and other numbers appear to play, very mysterious really, for different numbers of pegs and so on. But despite the Frame-Stewart approach being very natural, and despite all the available data suggesting that Frame-Stewart is always optimal, we may have no real hope of proving that this is the case. We may not see a proof of the optimality of our algorithm in our lifetime. If you're interested in finding out more, the by far most comprehensive account of what is known about the Tower of Hanoi is this book here. At this point, I'd like to thank Andreas Hinz, one of the authors of this book, for all his help and in particular for answering my super tower of questions. Oh, and if you're just itching for this video to end so you can go check out Doctor Who and the Celestial Toymaker, you may also want to check out my and Marty's book on mathematics in the movies and our mathematical complement to IMDb, the Mathematical Movie Database. There has got heaps and heaps of movies for you to watch. And that's it for today. Hope you enjoyed this video. Until next time, stay safe. Actually, let me really finish by showing you how to survive the final Toymaker boss challenge, moving our 10 discs via 5 packs using the least number of moves. This is super cool. Instead of just working with discs that combine into super discs, as with 4 packs, here we work with discs combining into super discs, which in turn combine into super discs. Enjoy!